So as was mentioned, application of all-polymer flexural plate wave sensors to polymer solvent characterization. So our objective here with this project is to develop a device and a method to measure the physical properties of polymer films in the presence of solvents. Applications for such a tool can be found in soft material characterization, chemical sensing, and biological sensing. Our solution, as shown here, is an all-polymer inkjet printed flexural plate wave sensor. It's framed in steel. That's not polymer. So a little background. Flexural plate wave sensors consist of a piezoelectric substrate, at least two sets of interdigitated transducers, and a sensing layer, often a polymer. So an acoustic wave is applied to the actuating IDTs when a oscillating voltage signal is applied. This wave will propagate through a sensing layer and the substrate to the detecting IDTs. And the wave velocity, frequency, and phase of that wave are determined by the physical properties of both the sensing layer and the substrate. This is about the same for a surface acoustic wave sensor as well. In general, for both surface acoustic wave, SAW, or flexural plate wave, FPW sensors, only mass loading of the sensing layer is detected. That is, when you expose the sensing layer to whatever your analyte is, you usually only detect the increase in mass in that sensing layer. So what we've done is we've fabricated a flexural plate wave sensor out of polyvinylidene fluoride as the piezoelectric substrate and polyethylene dioxythiophene polystyrene sulfonate as the interdigitated transducers, so both polymers. We then used this sensor, pictured in cross-section here, to measure the physical properties of a drop-cast polyvinyl alcohol sensing layer. And specifically, we did this by exploiting both mass and stiffness sensitivity of the device. This is exciting, as I just mentioned previously, because most FPW and SAW sensors exploit only gravimetric sensing. So just a bit of detail about the picture here. We have three sets of IDTs, one transmitting, two receiving, a drop-cast PVA sensing layer, and the PVDF substrate. So as I mentioned earlier, the flexural plate wave velocity and frequency, which we are trying to measure to detect something about the sensing layer, is determined by the physical properties of both the sensing layer and the substrate. Using Kirchhoff's plate theory, we can approximate the phase velocity of this wave with this relation here, and this is the phase velocity of the fundamental antisymmetric plate wave. And so this is phase velocity as a function of tension, so that's tension of both the sensing layer and the substrate, stiffness, and mass. In common FPW or SAW sensors, often like some of those that we saw today, or acoustic sensors like some of those we saw today, the substrate is so stiff that the sensing layer, if it's a polymer, any changes in that sensing layer related to stiffness or tension go undetected. That is, the frequency associated with these changes is completely washed out by any frequency change associated with the stiffness of the piezoelectric material. So given that we have fabricated a low stiffness substrate, the output frequency can be modulated by small changes in stiffness in the sensing layer and changes in tension in the sensing layer as well as mass. For a further theoretical description of this, please see Christoph Sielmann's work in the proceedings, Implications of a Low Stiffness Substrate in Lamb Wave Gas Applications, or check out his presentation yesterday. Our test setup is described briefly here. We input a 150 volt peak-to-peak 200 kilohertz center frequency signal with a wide bandwidth, and we detected a single output frequency, resonant sensors. And as we did this, we exposed a compressed air to the back, the sensing layer, with a 10% to 60% relative humidity. This is what we were investigating. And we kept the sensor at 25 degrees Celsius. So here's the picture of the sensor again. So I forgot to mention on the previous slide, we were measuring, what we're looking for is specifically how tension, stiffness, and mass change as a function of relative humidity when we expose PVA to increasing amounts of water. So as we increased the RH, we measured the shift in frequency, and we're able to detect how tension and stiffness changed. So a better description of how we did that exactly is given here. We had one sensor to which we applied three different thicknesses of PVA, 6.3, 9.5, and 12.6 microns. And for each of these three thicknesses, we exposed the sensor to different varying levels of relative humidity. We then looked we then looked to measure the properties of PVA thickness, which can be found in the stiffness, the relation for stiffness, Young's modulus, tension, mass loading, and partition coefficient, which is the ratio between the amount of solvent in the polymer and the amount of solvent in the ambient area. So in this case, the solvent is water. We did this by fitting the frequency results to the equation introduced earlier and using a Nedler-Mead solver. So the idea is we had a frequency shift, and we associated that frequency shift with not just mass loading, but also PVA thickness change, tension, and Young's modulus shifts. We then were able to compare these results with a few results obtained otherwise in other methods, so either by measurement or through literature. We couldn't find something that would be able to address tension, but we were able to compare with different values of thickness, density, Young's modulus, partition coefficient. So this plot here shows how we went about measuring the partition coefficient of our PVA sample. We simply exposed a sample of PVA to a constant relative humidity over a long period of time, measured its mass change, and used that to calculate the partition coefficient. Okay, so now that we have values to compare those which we are trying to obtain through fitting, we can look at our results. Now these are the sort of plots that we get. The plot on the left, this one right here, describes frequency shift and humidity as a function of time. So the blue curve corresponds to humidity, ranging from 10 to 30% RH. So this isn't a full sweep. We're just looking at a small region here. And then the green points correspond to the resonant frequency shift of the device. A few things to take away here. Number one, the frequency is falling. This is because there's likely an increase in mass. Also, there could be potentially a decrease in tension or a decrease in stiffness, but we'll talk about that a bit later. Also, the frequency, the resonant frequency, is quite low. That's around 200 kilohertz. And I say quite low because it's quite low for a resonator of this size. And the reason why that is because we have such a low Young's modulus. The plot on the right shows all the data that we collected with fit curves. Those are in black. And results from a COMSOL model presented by Christoph Sielmann in the aforementioned work. So if we take the results from the fitting curve, the fit curves that were shown here, we can make a plot that looks like this. This describes the percentage change of each of our properties of interest, so thickness, mass per unit area, Young's modulus, density, as a function of RH. The lines correspond to what we got from the fitting function, and the points correspond to those which we would have expected based on previous reports and our own measurements. So a few things to take away here. The relative change in Young's modulus was fairly close, or predicted relative change. However, thickness and mass per unit area were slightly off. Partition coefficient, which is shown here in the absolute values, as partition coefficient does not change as a function of relative humidity, and so could not be included here, was quite close. Perhaps a better way to look at it, though, is by the absolute error between the values which we predicted and those which we expected to get. And that's what this plot shows here, each of the property of interest, and then the percent error associated with the fitting values as they compare to those which we expect. So in general, the partition coefficient, dry mass, dry thickness values match experiment theory very well. Well, the Young's modulus, saturated thickness, and wet mass are off by up to 2 to 19%. So right now, we believe that our main source of error has to do with the type of polyvinyl alcohol that we use, as we know that it was not the same as that which we had used in the literature references, specifically its density, molecular mass, and hydrolyzation, or degree of hydrolysis, was different. Another factor which isn't accounted for here is a confirmation of how tension is shifting. While we did measure tension, we were unable to confirm exactly how tension was changing in the thin layer. So this could be contributing as well. So to summarize, we fabricated an all-polymer inkjet printed flexural plate wave sensor with a PVA sensing layer. We exploited the low stiffness substrate to measure Young's modulus, thickness, tension, and mass of the sensing layer as a function of RH. And then we compared a number of these values, finding that they agreed generally in the case of dry sensing, but in wet sensing they were off by 19%. And finally, we believe there's an application for this device in material characterization as a way to quickly interrogate the mechanical properties of a thin film in the presence of a solvent. So I'd like to thank these folks for getting us here and allowing us to do this research. So thank you.